Lesson 5.5, Curve Sketching. Curve sketching is a procedure for analyzing a function and its behavior without the aid of a graphing utility. We can use the relationships of f, f prime, and f double prime over specific intervals to quickly sketch the graph of the function y equals f of x. We already know how to find domain, range, intercepts, and asymptotes. In the last two lessons, we learned how the first and second derivatives can be used to determine four basic behaviors and curvature of a function. If we know the sign of f prime and f double prime over some given interval, we know exactly what the graph of f of x looks like on that interval. Complete the table below by sketching the general shape of the curve when each condition is met. So what we're going to do is we're going to think about what does it mean to have the derivative positive. That means that f is increasing. And to have the derivative negative, that means that f is decreasing. What does it mean to have the second derivative positive? That means concave up. The second derivative negative means concave down. So once we know those, f is increasing and concave up would look something like that. F is decreasing but concave up would look something like that. F is increasing but concave down would look something like that. And F is decreasing and concave down would look something like that. Example number 2, sketch a possible graph of the function y equals g of x that satisfies the following conditions. So the first condition is that the derivative is greater than 0 between negative infinity and negative 1, also from 3 to infinity. So I'm going to just fill in some things on this graph before we get started. And remember that g prime greater than 0 means that g is increasing. So that means that your function that you're trying to draw, g, is increasing from negative infinity to negative 1 and also from 3 to infinity. It is decreasing from negative 1 to 3. So I can imagine what's happening, but I need to read a few more things before I can actually sketch a graph. So now, the second condition. The second derivative is positive from negative infinity to negative 3. That is concave up. So we know concave up from negative infinity to negative 3. We also know concave up from negative 1 to 3. So it's increasing to negative 3, but it's still increasing from negative 3 to negative 1, but no longer concave up. Then it starts being concave down. So increasing and concave up to negative 3. Then we still are increasing, but we are concave down from negative 3 to 1. So concave down from negative 3 to 1, but still increasing, or negative 3 to negative 1. Because I know here this is concave down, and it says from negative 3 to negative 1. From negative 1 to 3, we have concave up again, okay? And it's decreasing. Concave up and decreasing. And then from 3 to infinity, we have concave down, but increasing. So Now, let's see the third. As I go to negative infinity, my g of x goes to negative 4. So that means that I want to put a horizontal asymptote here at negative 4. And as x goes to positive infinity, it goes to positive 4. So I want to put a horizontal asymptote here at positive 4. And then we are done. Now, what you could have done and what I did on my paper that might help you, I put negative 1 to 3 decreasing and, concave up. I put negative infinity to negative 1 increasing, negative 3 to negative 1 concave down, negative infinity to negative 3 concave up, and 3 to infinity increasing and concave down. So I don't know if that helps. I kind of, did it a couple different ways, but whatever you feel comfortable with, those take a little bit of time to think about, but the more you work with it, the better it'll be. So the function behavior chart from our previous lesson can be a visual aid to using proper vocabulary as well as helping us make graphical representations from verbal descriptions. And so these are all the things that we talked about before. Example number 3, can you sketch a possible graph of f given f prime? So if this is our derivative, we know that our derivative is 0 here and 0 here. Our derivative is 0, so therefore it's going from positive to negative. So that would be a maximum. So there's going to be a maximum here. And it's going to have slopes of tangent lines that are positive, and then it's going to have slopes of tangent lines that are negative, and it's going to go to a, going from negative to positive here, a minimum. So you knew you had a min here and a max here. So by drawing this max and this min, you can see that this could be a graph of f. So the zeros of f prime of x may be extrema of f of x. Extrema of f prime are possible inflection points. So what they mean by that is, and I'm going to go ahead and do this in blue, this extrema, which was your minimum of your derivative, ended up coinciding with a point of inflection where it changed from being concave down to concave up, right? So that was your point of inflection. When f prime of x is above the x-axis, then f of x is increasing. When f prime of x is below the x-axis, f of x is decreasing. So we saw increasing, and then we saw decreasing, and then we saw increasing again. So if f prime of x is increasing, then the second derivative is greater than 0. If f prime of x is increasing, then the second derivative is greater than 0. So f of x is concave up. And if f prime of x is decreasing, then the second derivative is less than 0. So f prime of x is, or f of x is concave down. Okay? Now, example number 4, connecting a function, the first derivative and its second derivative. Suppose the graph shown above is the graph of a function y equals f of x on the interval from -8 to 8. On what open intervals is f of x both increasing and concave up? Okay, so for this one, increasing and concave up, I see this piece right there where it is increasing and concave up, and I see this little piece right here where it's increasing and concave up. So I'm going to say on the open intervals from -5 to -2 and from 4 to 6. On what open intervals is f of x both decreasing and concave down? Let's do that in pink. So this one over here is decreasing and concave down. I see it right here. See how it's decreasing and concave down? I stop right here because then it changes concavity. Okay, so it's only decreasing and concave down for that piece. And so that would be from -1 to 2. At what x value does f of x have inflection points? Well, that's going to be where your concavity changes. Do you see right here how it goes from being concave up and it starts being concave down? So that means that this right here is a point of inflection. And then we've got concave down, and then all of a sudden now we have concave up. So this one is a point of inflection. And we've got concave up, and then all of a sudden concave down. So that one is a point of inflection. So at what x values? That would be at x equals -2, x equals +2, and x equals 6. If the graph above is the graph of the derivative, now we're going to pretend like this graph is the derivative. So I'm going to erase all the stuff that we did, because now we have to look at it for part B. What if this was our derivative? So I'm going to say that this is f prime of x. On what open intervals is f of x decreasing? Well, f of x would be decreasing where its derivative is negative. So do you see here where the derivative is negative? So it's going to be decreasing on 2, 6. I'm going to say 2, 6, and then I'm going to say where f prime of x is less than 0. That would be my justification. At what x value does f of x have a local maximum? Now remember, if you're looking at the derivative, to look for a maximum, you'd be looking for a 0, and where it goes from positive values to negative values, that would give you a maximum. Okay, and this one is the only one that is that way. So at what x value does f of x have a local maximum? And you'd say f of x has a local maximum at x equals 2 because f prime of x changes from positive to negative there. And then on what open intervals is f of x concave down? Justify. So if I'm looking at the derivative, I would be thinking of the derivative of the derivative to look for concave down, right? I'd be looking for where the slopes of my, where the slopes of my tangent lines are negative. So if you're looking for, look, negative, 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 and then it goes to 0, but from -8 to -5, the slopes of the tangent lines are negative, so therefore our original function is concave down. So that would be from -8 to -5. We would have concave down. Then the slopes of your tangent lines are positive, 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 positive. But then they start being negative, 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 negative. From -1 all the way to 4. So, and -1 to 4, we would have concave down. And then positive, 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 positive. So those would be the only two intervals. And what you would say, instead of talking about f double prime, since we don't know what that is, you talk about that because you know that if you took the derivative, the second derivative here, so the derivative of this derivative, it would tell you where it is increasing and decreasing, right? So, you know, that f double prime tells you where f prime of x is increasing or decreasing, just like our f prime of x tells us where f of x is increasing and decreasing. So every time you take a derivative, that derivative tells you what the one right before it is increasing or decreasing, depending on whether it's positive or negative. Whether we have a positive second derivative, that means that your f prime is increasing. A negative second derivative tells us that your f prime is decreasing. So we're going to use as our justification on this that f of x is concave down where f prime of x is decreasing. And so that is your justification. So at what x value, I'm going to use blue again, at what x value does f of x have an inflection point? So for this one, you're going to be looking at, because we're looking at the derivative, and so you're going to be looking, remember how we said that this, because remember, points of inflection are second derivative things. So if I see inflection point, I'm thinking second derivative. So if I'm looking right here at my first derivative, I again have to be thinking of slopes of tangent lines, right? So your second derivative, I'm just going to put f double prime here. It starts at -8. They're all negative to -5, right? Then positive, 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 positive slopes of tangent lines to -1. And then negative, 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 negative to 4. And then positive, 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 positive to 8. And at 8 you have a slope of 0. At 4 you have a slope of 0. At -1 you have a slope of 0. And at -5 you have a slope of 0. Okay, so you can put those on there if you want to. Those would be your critical points. And so for an inflection point, you would be wanting to look at whether it changes signs at the 0 of your first derivative, right? At the critical point of your first derivative, you're looking at whether the second derivative changes signs. It goes from negative to positive, so this one would be a point of inflection. It goes from positive to negative, this one would be a point of inflection. It goes from negative to positive, this one would be a point of inflection. So, I'm going to say, because it says at what x values? At x equals -5, x equals -1, and x equals 4, we have points of inflection on f of x, comma, because f double prime of x equals 0 at these x values, and f double prime of x changes sign from negative to positive, or from positive to negative. Now, you could be more exact if you want to and say, you know, it changes from negative to positive at x equals negative 5 and x equals 4, and it changes from positive to negative at x equals negative 1. You know, being more specific is fine, just don't be less specific. Okay, part C. Suppose the graph shown above is the graph of a function y equals f double prime of x on the interval from negative a to a. On what open interval is f of x concave down? Justify. All right, so now for part C, I'm going to come up here and I'm going to erase everything that we talked about, because now we've got a different situation. Now we're going to look at this graph as the second derivative. So that's going to change what we're thinking, and we can't keep those same things in our mind. Okay? That one's going to have to stay. Okay, so now, this is now f double prime of x. Okay? Oops. It kicked in. The eraser finally kicked in. Okay, so now we're going to answer these two questions at the bottom. On what open interval is f of x concave down if this is my second derivative? So think about it. If this is my second derivative, wherever my second derivative is negative is where I would have concave down. So I would have concave down, I'm just going to say, when f double prime of x is less than 0, f of x is concave down, comma. So it's going to be on the interval from 2 to 6. At what x value does f of x have an inflection point? Okay, so remember, we're looking for zeros here. Now, and then we're looking for it to change signs. So I have a 0 here at negative 5, but it goes from positive to positive. So this is not an inflection point, okay? Not a point of inflection. It's 0 here, and it goes from positive to negative, right? Plus to minus. So this one is a point of inflection. Here it's a 0, and it goes from negative to positive. So this one would be considered a point of inflection, okay? So you really have a point of inflection at x equals 2 and x equals 6. And the reasoning, hopefully you'll remember, the reasoning for the point of inflection that we know is because f double prime goes from positive to negative or negative to positive. So let's write this one. So we say f of x has points of inflection at x equals 2 and x equals 6, because this is where f double prime of x equals 0 and where f double prime of x goes from negative to positive or positive to negative. So it either goes from negative to positive or positive to negative, okay? All right. I don't know how much more you've got in you for this particular video. I know you're probably getting tired, and this is a long lesson. It looks like we have 1, 2, 3, 4 more pages. So what I might do is go ahead and stop this one